Hello students, welcome back to another lecture which happens to be the lecture number 5 in a series of lectures on classical mechanics for master degree students. And in the last class we stopped our lecture by giving what is known as a Lagrangian function, and we have given the name or the symbol for the Lagrangian function will be the calligraphic letter L. So that is going to be written like this, and the Lagrangian function is going to be a function of generalized coordinate, generalized velocity, and possibly time. So this is the place where we stopped in the last class, and we need a little bit explanation on this. Then we can proceed further in the today's discussion, namely the classification of dynamical system. So the title is written here on the top. We are planning to have a classification of a variety of dynamical system based on the appearance of the Lagrangian and based on some conditions. And that classification is only to help you to segregate the problems into somewhat easy problems, somewhat difficult problems, and some problems that poses impossibility to solve. So some of the systems cannot be solved because of some conditions. So this classification can be helpful for that reason, and that's what we are going to see. So L is written, this particular L, the so-called calligraphic or the script letter L is written only to say that it is a Lagrangian function. But otherwise, it is as simple as any mathematical function that you write using the letter F. So basically, it is going to be F of q, q dot, t. So when you are writing this particular last variable, I said that it is possibly time. I have used this particular word. So what is the meaning of possibly here is that time can be appearing in the function explicitly. Sometimes it will appear explicitly. Explicitly means the variable t should be visible in the equation. Once you write down the expression for f, in that expression t should be explicitly visible. So as an example, we can write like this: q square plus half q dot plus t. So this is an example. So this is an example of a function. You can write any combination of q, q dot, t, and this is one such combination. And in this combination, you can see that the variable t is visible to you. It is explicitly present. Sometimes it need not be present. For example, another example of this particular situation will be some, let me write down that some k times q plus we can write as q dot square. For example, this is another situation, or this is another example. So this is your example number 2 for the Lagrangian. But you can ask the question, t is not there in this equation, but how can you write t here? That is what I am trying to explain. Just because t is written in this Lagrangian, it does not mean that the t should be visible or it should exist in the expression. There is no compulsion. So that is why they say that this is a generalized form of writing. And in particular, t is now missing in this equation, the second example. So that is why we use the word possibly. Possibly means time may be present in some problems. Time may not be explicitly present in some other problems. So we have a variety of systems wherein the Lagrangian will be directly a function of time. Sometimes it may not be. So that is what we mean to say, or that is what we mean to explain by using a word possibly time. Okay, so let me again come back and then explain how can a particular variable will be absent here. That means the time part is absent here and still comma t is written here. How is that possible? So that is quite simple if you think, because there is nothing new here in the case of the physics. If you are going to take a simple mathematical example, for example, let me write down f of x comma y is equal to what is the meaning of f of x comma y? Write down any function of x and y. You write anything that contains x and y. That's all about it. One simplest example will be x into y. So this is an example. So let me write down that the first example of f of x comma y. The second example of f of x comma y could be like this, x square, and that's all. There is nothing wrong. If the first one is a correct expression for a function of x comma y, the second example is also a correct expression. This is also correct. There is nothing wrong here. You should not say that y is missing and therefore this y should be removed in the left side. It is not necessary. That is the point I am trying to explain. So for comparison, let me also write down f of x equal to x square is also correct. This is correct. It's a function of x alone. The second point I am trying to explain is f of x comma y can also be x square. This is also perfectly correct expression mathematically. Similarly, we can also write down f of x comma y comma t equal to x square. This is also perfectly acceptable one. Which means that you can clearly see that the y and t, these two variables, are missing on the right hand side. In this expression, y is missing. So even then, we can always say that it is a function of several variables. Now, how do you understand that it is possible is, it's quite simple. If you really want to have the appearance of the y in the expression, then you put a y to the power 0. And that's all. Now I will say that y is visible. So y to the power 0 is 1. So x square into 1 will give you x square. That's what I have been telling. You have an x square here. So this expression doesn't contain y means y is present, but it is invisible. That is what I mean to say, invisible. Therefore, you can always write down a comma y here and y will be missing here. And this is not the only reason. By you should always not try to put a power 0 and then make it present there. It is not compulsory. For example, you take this particular example, third example I'll write down here. If I am going to write f of x comma y comma t, for example, equal to x square. Now, this y and t are not explicitly visible. One possibility to make it visible is to put y to the power 0. This is fine. Y power 0 you can substitute. And now I can say that y is visible. And if you simplify, y will be invisible. That's fine. But what about t? T to the power 0 I can write. But everything you should not consider that only multiplication. Because function means you can add, you can subtract, multiply, divide, power, whatever you can do. So y should always multiply. If I am going to add like this, for example, can I write a t to the power 0? You can't write. If I write t to the power 0, then this becomes 1. So this is 1 plus x square. 1 plus x square is not the original expression. You got the point? 1 plus x square is not the original expression. Our original expression is only x square. So how will you manage to bring this kind of scenario? Is very simple. That it doesn't matter what kind of power you have. What you write, whatever power that you have, t to the power 1, 2, 3, whatever it is, you write 0 into. Now I can say that in this expression t is visible. It is explicitly visible here. But if you simplify, you will get back only x square. So therefore, this is very elementary concept of functions. So basically it means that when you write f of several variables here, on the right hand side, there is no necessity or there is no compulsion that every variable should appear there. There is no such compulsion. Okay. Many of the variables can miss, but even then it will be considered as a function of that many number of variables. So this is a very crucial point that should be clear to you. This is and that is exactly what is now required to explain the word possibly time here, because mechanical systems or dynamical systems will be sometimes explicitly the equations will have t, sometimes in many cases t will not be there in the equation. So this is the point or a basic point that you should remember. Okay, so let me erase this portion of the board. Fine, now we are back to the original place where Lagrangian is a mathematical function. So let me again tell you what is meant by Lagrangian. Lagrangian, we need not tell every time Lagrangian function. The word function is not necessary. You have to write every time. You simply write down Lagrangian. So the word function need not be written. Okay, when you are learning for the first time, you say that it is a function of 3 variables. That's what we mean to say. And later you simply say that it is a Lagrangian. So we understand that it is a mathematical function of 3 variables and possibly some of the variables may be absent. In particular, time will be the situation in practice. Mathematically speaking, any variable can miss. Okay, the most simplest expression that I can write for the Lagrangian of q comma q dot comma t, where all of them will be disappearing, is 1. L of q comma q dot comma t equal to 1. This is very much mathematically acceptable function for L. Physically, whether it is acceptable or not, or which dynamical system will have L equal to 1, that is a different question. That I am not coming to the picture. I am talking in a pure mathematical term. Whether a mathematician will accept a function of 3 variable to be equal to 1, that's the question. The answer is perfectly yes. You should not say that q dot and t should be present on the right hand side. The reason is you can always write down that this is 0 times q plus 0 times q dot plus 0 times t. So that's all. That is the meaning of that. So q dot and t are present in the equation, but they are present to the extent of, oh sorry, I have written 1 here. Therefore, one of them you have to make an adjustment. You can make the adjustment for any of the variables. For example, I can write down that this is 1 into t power 0. Okay. So which means that you can also accept 0 as a possible answer. That is, you understand that. So any function 0, 1, constant, all of them are acceptable functions of a 3 variable problem. So that is a point that I am trying to explain. And why we are very particular about writing possibly time is because out of the 3 variable, most probably time appears in some problem, time doesn't appear in some problem. That is why specifically we are interested in time, okay, instead of q and q dot. Generally q and q dot, they are present in almost every problem it is present. So that is based on physics. Mathematically speaking, everything can be absent. Okay, so mathematical thing is very still more general situation, and in most of the physical examples, q and q dot will be present in the expression for the Lagrangian. Only t may be present, may not be present. Let us come back to, so because of that, what happens is we are interested to classify the dynamical system based on the way in which these things are appearing. So especially what happens is when a particular dynamical system is independent of time. So that's what I will write down here, that if it is going to be, let me erase this portion also. So we can now make, at least we can make 2 of the classifications like this, that I will write down here that if t is absent, or t is absent is in a way of, mathematically speaking, t absent. Physically we say that independent of time. If this particular expression is independent of time, then, so this is the condition. So let me, if you want to have some kind of flowchart like appearance, you can put a box, but that's not necessary. So we are simply saying that 2 classifications where the time is absent in the expression, or in other words, a particular dynamical system, the expressions are independent of time, then these are known as autonomous dynamical systems. And the other possibility is very clear if time is explicitly present. So that is the condition. So if this particular condition is satisfied for the dynamical system that you are planning to study, then we will categorize them under the name non-autonomous dynamical system. So this is important terminology, because why do you want to, first question is why you want to make all this classification. We can consider all the dynamical system under one heading and then keep learning them. So what is the purpose, or what is the point in making all this classification, is that the reason behind this is that the mathematical method for the solution, because ultimately you should remember that a dynamical system is going to be written down in the form of a set of coupled differential equation, and ultimately if you want to study the dynamics, the meaning is you have to solve it. The solution of the differential equation is going to speak about the dynamics or the behavior of the dynamical system. So ultimately, we need to get the solution to the differential equation. And at that time, when time is present in the equation, the methodology of the solution is different. If the time is absent in the equation, the technique that you are going to follow to get the solution is different. So you are not going to apply the same methodology to get the solution when t is present and when t is absent. And because of that reason, we separate them. So that when t is present, the equations are going to be complicated, solution methodology may be more complicated, and so on. Whereas when t is explicitly not visible, okay, when t, that is the explicitly is very important term rather than saying independent of time. So this word independent of time is some kind of, that's why I have written, you see this inverted comma. So something like, when you put something under the quote, it looks like, you can imagine as if it is independent of time. That is what I am trying to say. So to be more precisely or to be mathematically accurate, t will be absent in the equation. Instead of saying absent in the equation, you say that explicitly not visible. So this terminologies, you have to be more careful. So let me write down, the word absent can also be written down as not explicitly visible. Why you have to be so careful in writing not explicitly visible, or why don't you say simply independent of time, is that there is something which you have to be very careful. We are talking about dynamics, right? Dynamical system means what? Dynamics. Dynamics means what? Something has to change with respect to time. If time is changing and then nothing is changing, means it is not at all dynamics. It is actually the problem of statics. So this is a very fundamental thing. So therefore, when I am saying, or when we are saying that we are going to talk about the dynamical system, and then you say that independent of time, then there is something contradictory. Okay, it appears as if you are making some mistake. So remember, dynamical system in time has to enter. Something is changing with respect to the time. D by dt is there. If d by dt itself is not there, then where is dynamics? Everything is statics. Statics means constant. Only time will change. Physical system will not change. That is the static situation. So you have to be very careful in using this terminology, that since the moment you are saying that we are talking about the dynamical system, there is something changing with respect to the time. If it is so, how can you say that this is independent of time? So that question will come. So that is why I put an inverted comma here. The meaning is that is something equivalent to saying that the time is absent in the system. By that, what exactly we mean to say is, it is not explicitly visible. This is more accurate. This particular statement is more accurate. Instead of saying independent of time or absent, not explicitly visible is a better word. Now, by that, what is the meaning is that even though it is not explicitly visible, d by dt is present implicitly. So that is the ultimate conclusion. So you cannot say that time has nothing to do with the system. Then it is totally wrong. The dynamical system has to do with time. That is why dynamics is going on. Explicitly, t is not visible. That's all about it. But implicitly it is there. So the implicit and the explicit concept should be very clear to you. Okay, that means some kind of indirect influence is going on. Directly, t is not visible in the equation. Visible means where it is visible. In the equation, it is not visible. Okay, but time is there in the controlling of the system. So it is somewhat invisible. That is what we say. Implicitly, it is present. So the word implicit, explicit is very important while defining the autonomous and non-autonomous system. So a rough way of saying is only independent. So I will not recommend strictly saying independent of time, but the better methodology would be to say not explicitly visible, but however, time controls in an implicit manner. Okay, it is there indirectly. So this is the fundamentally very important broad, or this is the main classification into the two varieties. And most of the time, okay, 99% of the problems that we are going to discuss would be the one corresponding to the autonomous dynamical system, because that is the one in which the time doesn't appear in the equation, and therefore when something is not there in the equation, then it will be somewhat better and easy to solve. So that is the reason. Remember that The most simple things that we are going to solve are the ones that are recommended. The so-called, you are also going to study the Goldstein book in particular. So most of the problems that you are going to study will correspond to a situation where T is absent. There may be some one or two example problems or one or two exercise problems or will be there in order to demonstrate how complicated the things will go when T is present in the system. Okay, so that is what is the meaning that you should remember. And after reading the standard book by the Thornton and Marion, you should again come back to the Goldstein book on classical mechanics, because that is the standard recommended book. First time reading may not be comfortable, but once you understand these things, second reading would be comfortable for you. So you have to come back and read the Goldstein book. So that is important. So the ultimate thing is that all majority of the systems that we are going to concentrate will be coming under the category of autonomous dynamical system. This is the first point that you need to remember. But for the case of examination, like if you are writing NET or CSIR GATE examination, there may be an objective question. Okay, non-autonomous system means what? 4 options can be there. Time present, time not explicitly not present. Some 4 of these options can be there. And it is easy to confuse or it is easy to forget this simple thing. So there may be a possible question in the competitive examination. And therefore, classification is very important, both for the purpose of this examination and for the purpose of knowing what technique that you want to do for the solution. Okay, so we are not going to discuss more about the non-autonomous because the methodology, solution technique, all things will get complicated, and in your MSc program it is not there. So this is a main classification. Okay, there are further classifications are there on the dynamical system. So let me erase this portion, or I will come down here and then discuss further classification. Now, further classification of dynamical system is based on what is known as constraint on a dynamical system. So when you are having a physical system that we are planning to study in classical mechanics, then there may be constraints. Constraint means some kind of restriction. That restriction you may be imposing on your physical system that you are doing in the laboratory, or such constriction or such a constraints may be present naturally. It can happen anything. If you are going to study some natural phenomena like the dynamics of planets, okay, how the planets are moving under the influence of gravity, that's a natural system. So you are not going to put any restriction. That is one thing. Second thing is you may be performing some experiment in the laboratory, for example, a simple pendulum. And you can ask the question, is there any restriction or no restriction at all? That should be clear. So in order to distinguish or in order to further understand the nature of the system, we need to know whether any constraints are imposed on the system or not. Constraint means restriction. Restriction on what? Restriction on the motion of the system, because something is moving. In the case of the simple pendulum, the bob is oscillating. Oscillating means moving. It is moving from one place to the other. Are you putting any restriction or no restriction? That is the question. So if you take this particular example, the simplest example, if you take, you can easily understand what is happening. So if you are going to consider the case of the simple pendulum, then you have to tell whether constraint is there or not there. So the oscillation will be taking place in this direction and then return back. That's fine. Everything is fine. Now the question is yes or no. Is the restriction imposed or not imposed? So the answer is yes. So constraint is present in the system. Yes, it is present. So next question is coming. What is the constraint? What kind of constraint is there? That is the answer is that first thing that is happening is that the oscillation takes place in a plane. Oscillation means the word oscillation is fine. That is fine. But actually what do you mean by that is this particular bob, when it is moving, when an object is moving, is it moving in the 3 dimension, or is it moving in 2 dimension or 1 dimension? That is what we are very particular about. That will tell you whether the constraint is there or not. First, let me tell you what is meant by no constraint. No constraint means you take a butterfly. Okay, butterfly is flying in the space. Are you putting any constraint? No. So it can move in the 3-dimensional space. So the x, y, z, 3 variables or the 3 parameters will tell the location, the point P. So if you take a snapshot of the flying butterfly, then at that particular instant of time, the location of the butterfly is given by 3 parameters x, y, z. And therefore, you can say that naturally this is a 3-dimensional system, therefore 3 parameters are there. And are you putting any restriction? Means no, we don't restrict, it is flying on its own. And when such a situation happens, you say that constraint is no or absent. So there are some dynamics where constraints are absent. Okay, so you must be able to clearly distinguish between yes or no constraint. If it is no, okay, the problem is you can quickly classify the problem and proceed further. But if it is yes, then you have to tell what kind of constraint is there and you have to give further details. That is what I am trying to say. Okay, if it is no, 0 constraint means fine, that is straight away the problem is a 3-dimensional problem for one particle system. Remember, 3 is for one particle system. If 2 butterflies are flying simultaneously, and if you are going to take a snapshot of that, then I will be having P1 will be the position of the first butterfly. I need x1, y1, z1, and this at the same time there will be another butterfly located in a different position whose coordinates are x2, y2, z2. So automatically, how many numbers are required? Means 3 for the first butterfly, 3 for the second one, 6 numbers are required. So that 6 number is what we are planning to talk about, the degrees of freedom of a dynamical system. We are going to use the word degrees of freedom. So 6 is the answer for a 2 butterfly system. If 2 butterflies are flying freely without any restriction, the number of degrees of freedom is 6. 3 for first one, 3 for second. So that is a very simple situation where constraints are not at all there, or there is no restriction at all. But now we are asking the question, suppose if there is a restriction, what happens? That is what I am trying to explain. So now in the case of the simple pendulum, because you know what a simple pendulum is, you have seen it, you have oscillated, and so what is happening, everything you know. That's why I am taking this example. So constraint is present means yes. What is the constraint that is present, or what is that you have imposed when you are performing an experiment is that you must allow the oscillation to take place in a plane. So oscillation takes place in a plane. That is important. That means when you are performing the experiment, the bob should not oscillate like this. So I'll now write down trajectory, for example. So the bob should not oscillate like this. You can also make the bob to oscillate like this, make a complete round horizontal plane. You can oscillate like this. It can go round like this. If it is going like this, you can always draw something like a cone. You can draw something like a cone. That's a part of the cone. If you allow the pendulum to oscillate like this, then it is not a simple pendulum. Okay, the word simple is there. Why it is simple is because of that reason only. You are restricting to oscillate in a plane. That is why it is simple. If you allow it to oscillate anywhere, then it is a non-simple pendulum. That is actually a complicated pendulum. Okay, we don't use the word complicated pendulum because calculation goes complicated. What do you mean by that is you writing down the equation of motion itself becomes complicated. In particular, if you are going to allow to oscillate in a cone, then it is known as conical pendulum. If you arbitrarily oscillate in any structure, then it is completely, you can't give any name. Okay, that is the situation. So simple pendulum is one where you are very particular in oscillating the bob to oscillate only in a plane. That means when it is coming like this, so it will come here. So then the rod of the bob will be here, the bob itself will be here. And similarly, when it is here, this will be the rod, and here you will have the bob. And if you are going to give a color, or if you are going to shade this region, that should be a plane. So plane means you should know. It's a mathematical plane. It's a sheet of paper which is not bent. Okay, paper should not bend in a curved structure. Then it is not a plane. It's a curved surface. Plane means no curvature. So when the bob is oscillating from the leftmost edge to the rightmost edge, and if you are going to cover the entire region, that entire region, if you are going to give a color, that becomes a surface, and that surface should be a plane without any curvature. Only then the experiment that you are performing is a simple pendulum experiment. Otherwise, no. So this is the restriction. So under that condition, you have to perform the experiment, and therefore there is a restriction going on in the system. So that is fine. Now, why do you want to discuss this? Why this is important? If restriction is there, what is going to happen? Is it going to make the problem more complicated, or that it is going to help you to solve the problem easily? Which side it is useful? Is it going to create additional difficulty, or it is going to simplify the problem? So that is the question that we have. The answer is, if constraints are present in the system becomes somewhat simple. That is the answer. Okay, which means that indirectly, what it means to say is that the originally three-dimensional problem. What do you mean by originally? Originally means zero constraint. You don't impose any constraint. Allow the bob to go anywhere. Then x, y, z will be the three coordinates required to specify. It is not a simple pendulum, that is okay. But you will be having three variables will be coming into picture, x, y, z. So you will have to write down the Newton's equation for the x, and for the y, and for the z. That's the meaning. Newton's equation, when you write, it's a vector equation. So automatically you have to write down three equations, one for each component. And therefore, when zero constraints are present, which means that the restrictions are absent in the system, the number of dimension is 3 for a single particle. You remember, it's only for a single particle. So now, what is the job of the constraint is that this will get subtracted. Now, three-dimensional system will reduce to a two-dimensional system if you are going to impose some restriction. And if you are going to impose much more restriction, two-dimensional problem will become a one-dimensional problem. And if you are going to impose further and further restriction, this will become a zero-dimensional problem. So what do you mean by that? What is meant by zero-dimensional problem is that if you are going to have an x-axis like this, the particle will be here. This is your particle or the bob. Zero dimension means I impose the restriction in such a way that this bob should not move anywhere. I put restriction on left side, right side, top and bottom. I hold it in one place. It should not move anywhere. That is a restriction. If I restrict in such a way that this particular particle should not move anywhere, then this is an example of a zero-dimensional problem. That means you don't require anything to specify its dynamics because it is going to stay there. That's all. Only time will change. This particle cannot change. So you don't require anything further. So the problem has become very simple, and you don't require a Newton's law at all. That you can see now that the problem has become simple. What is the most complicated situation is where you don't impose any restriction and allow the particle to go anywhere, and therefore you have to run behind the particle, capturing the position of the particle and find out what is the acceleration, velocity, etc. So that is a difficult job. So therefore, solving a three-dimensional problem is difficult. Solving a two-dimensional problem, yes, a little bit difficulty has come down. Solving a one-dimensional problem is easy, and there is nothing to do in the solving of the zero-dimensional problem. Which means that in every arrow that I am going to put here, there is a restriction. So this is what we mean to say, some constraint is written here. And similarly, here also additional constraint, here also additional constraint. That is the meaning. And therefore, what happens is, in this particular situation, in the case of the simple pendulum, also a similar situation has taken place, that the particular oscillation takes place in a plane. And this is the first situation that you are visualizing. The realistic situation in the case of the simple pendulum is much more restriction or much more constraint is taking place. If you think only, you can observe it. What is that additional constraint that you are going to have? Okay, so let us further examine what is the meaning of oscillation taking place in a plane. So let us say that this is a plane. I'll write down that that is a plane that I have. So you can always take some solid material, like aluminum sheet. You cut it in this particular form. This aluminum sheet you take, and that's a plane, mathematical plane that you have. And now you have written that the oscillation of the bob takes place in a plane. Now mathematically it means that the bob can come here. The bob can come here. Oscillation means moving, right? It can move anywhere. So where and all it can move is, these are the possible places. Anywhere it can move. As long as the bob is going to be on this particular plane, it can come anywhere. That is the meaning. Mathematically speaking, that is the meaning. But however, in an experiment, whether bob goes here, the bob will never come here. In this region, bob will never come. So where will be the bob? What are the possible positions for the bob? This is another position. This is another possible position. So I am now showing the possible positions where the bob can come. Whether the bob can come here? No, it cannot come. Whether the bob will come here? Here also it cannot come. So these are the places where the bob cannot come. Here can the bob come? No. At this particular place, the bob will not come when you are performing simple pendulum experiment. And therefore, it means that the restriction that you are going to impose is much more stronger than what you have written. So therefore, oscillation is taking place in a plane. Yes, that's fine. But even more restriction is going on in the system. So what is that restriction? The answer is that the bob or a particle, let me generally write down, instead of bob, I will write a particle. The particle in the system is allowed to move on a circular path. Only. See, allowed to move only. That is the place where you have to catch the restriction. That means it is not allowed to move any other place. That is the meaning. Is allowed means in some other places it is not allowed. And the word circular is the place where you catch the mathematics. Because simple pendulum is fine. That is experiment you do without worrying much about the mathematics. Now that this is a mathematical formulation of the experiment, the word circle is the one that brings you the equation. So where is the circle here in the case of the simple pendulum is that if you are going to complete this particular path, say if you are going to complete this, how this particular path will look like? This is supposed to be a circle. This one. So whatever that you are having, that if you are going to oscillate like this, it's going to be a circular path if you draw properly. Which means that you can allow the bob to come here, you can allow the bob to come there. So these are the possible positions where the bob can go. It is possible, but even though you don't take them all the way up here, we ask the question, what is this? What is this kind of a path? So this kind of a path is part of circle. So this is the important thing. The part of the circle, the word circle is the place where you bring an equation. And the moment you understand that this is a circular path, the equation that is to be written down will be x square plus y square will be equal to r square, where r is the radius of the circle. But where is the radius of the circle here? That is clear that if this is the point where you are hanging the bob, and that will be the L. L means it is the length of the pendulum. So therefore, this particular radius of the circle should be the length of the pendulum. So therefore, we can write down that x square plus y square would be equal to L square. That would be the equation of the circle. So therefore, ultimately what happened? That is what we want to know, what happened finally. We are interested to know whether the three-dimensional situation, you remember three-dimensional is the highest situation where the constraints are absent. So 3D will come down to 2D, 2D will come down to 1D. This is always there, and 1D will come down to 0D. Now our question is, the case of the simple pendulum, where it comes, whether it is here Answer is no, it's not 3D. That you already know because it is oscillating in a plane. Plane means what? 2-dimension. Okay, 2-dimension possibility is there. Its possibility is there. But however, you have written a B here. So B tells that we are going to put much more restriction. It is not going to move in a plane. So even the 2D is gone. Now our restriction is much more tough that it is supposed to move on a 1-dimension. But how do you say it's a circle is written? How can you say it is 1-dimension? Is because out of the two variables x and y, one depends on the other. You see what is the meaning of this? That when you write the equation x square plus y square equal to L square, you have to be careful whether x comma y is independent of each other or x and y are dependent on each other. You don't require x and y. Both of them are not required. So that comes down to either x or y. This comes down to, we say that this is reduced to one variable. X comma y means two variable. When it is two variable, it is 2-dimension. That is also now reduced to one variable. How it is reduced to one variable is because of this length. Because the length is fixed here, it is going to move along the circular path. So it is going to travel on a particular line. It's a path. Path means always linear. Well, the linear is the word that you have to be more careful, that it need not be straight line. Okay, it's a curved path. So curved path, what happens is, interestingly, this is the place where you have to think in terms of what is called the polar coordinate system. So what happens is, when the Cartesian coordinate system, you will be converting this x comma y to the case of r and the theta, because this is a plane polar coordinate. Now 3D is not there, so don't worry. When 3D is there only, you have to think about spherical polar coordinate and cylindrical coordinate. Now you already know that the plane, it is restricted to plane, so automatically it is 2D, and then you are reducing further. So there is no need to worry about 3D polar. We write down only 2D polar. 2D polar is also known as plane polar. For the plane polar coordinates, r comma theta is the one that is already familiar right from school that you do. So x comma y is basically rewritten or equivalently converted to r comma theta. Okay, but what is r? R is the radius of the circle, that's fine. But in our example problem of simple pendulum, it is the length of the pendulum, comma, theta is fine. But what is the length of the pendulum? Will it change? When the pendulum is oscillating, L will not change. When the pendulum is oscillating, L will not change. Therefore, this is a constant. So when it is a constant, automatically happens. Only variables only you have to worry. Let there be 100 constant in a problem. That is not going to make your life tough. Only the number of variable is the one that is going to make you struggle. And therefore, L being a constant, then how many variables are there? This is the only variable that you have. This is the only variable, and therefore we say that the simple pendulum is a one-dimensional physical problem. So now you understand whether constraint is important or not. Constraint or the restriction in a particular dynamical system is very, very important. And why it is important is, it is going to help you to reduce the number of degrees of freedom. Our conclusion is, it is going to reduce the number of degrees of freedom. And if the number of degrees of freedom reduces, why should you be happy? Why you have to be happy means, this is very important. Why you have to be happy means, the number of equations to be solved is reduced. That is the meaning. 1 degree of freedom means 1 equation, 1 Newton's law you have to write. Another degree of freedom means another Newton's equation you have to write. 3 degrees of freedom means 3 Newton's law you have to write. One for each component. I think you are comfortable in this statement, otherwise I'll write down. When you write F equal to ma, what I am trying to say is, this is not a single equation. F equal to ma is not a single equation. It is a set of 3 equations. So where is the set? For the x component, you have to write down like this. Fx in the I direction is equal to mass times acceleration. Sorry, I will write down like this. It is the acceleration in the I direction. Okay. It is the acceleration in the x direction. I is the unit vector. And for the y direction, you have to write like this. Mass will not change when the direction is changing. So I am keeping the same mass here. And then you have the acceleration in the y direction multiplied by the unit vector. That means that particular component. And coming to the z component, we can write the z component along the k direction will be mass times acceleration in the z direction in the z direction. So therefore, I will put a bracket here. So the 3 equation is what we write F equal to ma. F equal to ma is not a single equation. And this is what is known as 3D. So since you have written 3 equations, this is called a 3D problem. So if you want to solve a 3-dimensional problem, you have to write down 3 equations, 3 Newton's equation, and you have to solve. And once again, where is the difficulty comes interestingly is that this is not an algebraic equation. You see, you should not think that this is that simple. It is not that simple. When you take a first equation, when I say that fx equal to m times ax, say I and I you can cancel because that is the same thing. So what you have is this much. And so what is there to solve here means it's only an algebraic equation. It is not so. Here only you have to be more careful. This is not a simple algebraic equation because acceleration is a second time derivative. So remember that this has to be written down as d square x by dt square. And here the force is not going to be a simple force. It is going to be written down as a negative gradient of a scalar potential. So we express the force in terms of potential, and you know that force is equal to negative gradient of scalar potential. And this is the equation that you have to solve. This is called Newton's equation in one dimension. You see, this is not a simple equation. There is a x here and there is a t here. There are 2 variables are involved in the problem. That is fine, but at least the thing that is to be solved is for x, and therefore it is a second order differential equation. At least to that extent the complication is there. It is a second order differential equation you have to solve. Like that 3 of them you have to solve. And therefore, when you have a 3-dimensional problem for a single particle, remember this is for a single particle. For a single particle, the solution requires solving 3 of the second order differential equation. And therefore, you have that amount of mathematical work is there behind you. Okay, you might not have solved, that is different. But if you really want to get the solution, then you'll have to solve 3 of them. And therefore, now in the case of the simple pendulum, what happened, we'll see. The 3-dimensional, originally 3-dimensional system has come down to 2-dimensional because it is oscillating in a plane. And since the length of the pendulum is constant, this 2-dimensional system has come to a 1-dimensional system. So the arrow is here, then the arrow is here, then the arrow is here. So here it is there. So after that, the arrow has come here. From here it has come, the arrow is here, and it has come here. So ultimately you have a 1-dimensional problem, and therefore you will be solving a single equation for the simple pendulum. And that is what you are actually solving. Even that solving is not easy thing, that I will tell later. But for the time being, I will tell you that for the case of the simple pendulum, we will be having d square theta by dt square will be equal to something. So you see that this particular x is, for the case of simple pendulum, it happens to be theta. And the reason is, just now I have explained that you are basically converting. Here it is there. So this is the theta is the only variable, and for that only variable, you have to write down the Newton's equation, and that Newton's equation is what is going to look like d square theta by dt square will be equal to, right hand side you have some expression, and for which you, and from there you calculate the time period t equal to something square root of L by G, 1 by 2 pi, etc. And that too after some simple assumptions. Okay, solving that is also not a trivial and simple job. That part I will tell you later. Now the important conclusion that I want to tell you is that you see how the constraint or the restrictions on a physical problem helps you to reduce the number of degrees of freedom. This is very crucial, and for this you see how much you have to think. You have to carefully think in order to say that simple pendulum is a 1D problem. Otherwise, it is most probably you will make a mistake that it is a 2-dimensional problem, because x comma y is there when something is moving on a curve. This is x1 y1, that is x2 y2, that will be x3 y3, and that will be x4 y4. So you generally think that 2 variables x comma y is required. But if you make a transformation to the polar system, 2 dimension has been reduced to 1 dimension. Therefore, the mathematical coordinate transformation is also going to play a very important role, and that is the reason why people choose, or that is the reason why people prefer one coordinate system in place of the other. Not just we want to do a coordinate transformation and go to another coordinate. Not for just for doing, but there are reasons are there. Some problems will become simple when you move to another coordinate system. That is exactly the reason why we have various coordinate systems. Okay, so this is a very important point that I would like to tell. And next, let me erase this board and then tell you the classification or the terminology that we are going to use when the constraints are present in the system. So that we will see now. So here is the classification that I am planning to explain. I have only written down the dynamical system as the main topic to be classified. And till now I explained that there are two main cases where constraints are going to be present. That's what I have written here. And another situation is where the constraints are going to be absent. That's all. That is the main classification that you are going to have. Further classification I will explain. But before that, let us now finish what is to be written under the no constraint condition. When you are not going to impose any kind of restriction on a dynamical system, then in the case of the particle dynamics, we will be having the full 3D problem. That means there is nobody is there to reduce the number of dimensions. 3-dimensional will not come to 2-dimensional and so on. So nothing is going to reduce, which means that the full 3-dimensionality will be there in the problem, and therefore the full complexity will be present in the system. So constraint, you should remember what is that happening. Constraint is going to help you to reduce the number of dimensions, which means reducing the number of degrees of freedom, which means reducing the number of Newton's equations to be solved. Therefore, constraint is going to help you to simplify the problem to a great extent. That's the conclusion. So if there are no constraints, and when you are allowing the system to move freely in the space, and the space being the Euclidean 3-dimensional physical space, then you will be having the entire full 3-dimensionality will be the available freedom to the system. And therefore, I can write down that the number of degrees of freedom I can write as DOF. Number of degrees of freedom would be equal to 3 per particle. So I can write down that this is 3 per particle. So what is the meaning of that is, if there are n number of particles are there, this means if there are n number of particles are there, then the number of degrees of freedom would give you 3 times n. So 3n we can write where capital N is the number of particles in the system, in the physical system. And the word particle is very important. Okay, particle dynamics is different from rigid body dynamics. So that difference is there. You please remember this. I will explain when a suitable time comes. So it is per particle. If it is not particle, then additional degrees of freedom has to be added to the system. So that point is to be noted down. And once this is clear, and the discussion is almost over for the case of no constraint condition, because there is nothing more to reduce, and therefore consider the full 3-dimensionality, write down all the 3 Newton's equation of motion, one per direction, and start solving per particle. That's all about it. Now coming to the next case where the constraints are present, and you know that present means you know that there is a constraint. But the problem is that you may be knowing what is the constraint. You know that I am going to impose some kind of restriction on the problem, but however, I may not be knowing what is the equation of constraint. That's what I have written here. In the previous example that we have been discussing on the simple pendulum case, you know that the particle or the bob is going to be considered as a particle and not a solid object. So this technical point has to be clear here, that in the case of the simple pendulum problem, the so-called bob is going to be considered as a particle. If it is not going to be considered as a particle, and if you are going to consider it as a solid 3-dimensional sphere, if you are going to consider like that, then there may be additional difficulties such as moment of inertia and other things will enter into picture. So those things like moment of inertia will not enter into picture when we are studying the particle dynamics. And therefore, we are going to make an assumption that this is going to be a particle. So if it is the case, you need to know whether the equation is known or not. For the case of simple pendulum, you know that it is going to move along the circle, and you have also written down the equation of circle, isn't it? So there are many situations where you do not know the equation of constraint, but still you know that there is a constraint present. Like that, many situations are there. You consider, for example, I will write a schematically. I'll draw something like this. So I have something like this, some part of rock. For example, you have some kind of a rock, or you can consider that this is a hill, for example, and then you have certain object. I have a particle which is sliding down like this. So you consider that this is sliding down this particular rough surface. So some surface is there which is not well defined. Okay, it is not a plane. It is not coming on a circular path. There is no well defined path. Okay, somewhere so ups and downs are there, and therefore, but it is clear in this particular example is a clear example where there is a restriction present. How do you know that restriction is present? Means this particular object has to slide on the surface of the hill only. So on the surface of the hill, that is the construction. It cannot jump like this and then fall down like this. That is not going to happen, isn't it? So that is a restriction. You are posing the imposition, or you are demanding a condition that the particle has to slide on the surface of the hill only, and therefore that is a restriction. So restriction is there, that much is clear. But if you ask what is the equation, I don't know the equation of the surface. So you have a surface, right? The hill surface that you have here, I will write down here, for example, equation for surface of the hill is unknown because it is complicated. It doesn't fit into a simple standard equation of a plane, parabola, hyperbola, some kind of standard surfaces in the mathematics. No, that nothing will fit into this. And therefore, the equation of the surface is complicated, which we do not know. In that particular case, we will be coming into a scenario that is written in this particular box. You read this, equation of the constraint is not known. So this is a situation, a physical problem where it comes under this category. If it is so, we will give the name as non-holonomic system. So let me write down the classification. This is known as non-holonomic system. So this is one main or major classification, because instead of asking the question, do you know or not, it is easy to say whether you do not know or not. Okay, certain things are mathematically we do not know what is an expression or what is the kind of equation that we are going to have. When certain thing is very clear that you do not know the equation, but still you know that there is a constraint, such situations are known as non-holonomic constraints or non-holonomic system. We can say non-holonomic constraint, or we can say non-holonomic system, because you do not know the equation of the constraint. You can use the word for system or constraint. Okay, non-holonomic constraint, you can also use that word. So this is a scenario where the constraint is not going to help. Ultimately, what is the meaning is, even though there is a constraint present in the system, that constraint is not going to help you to reduce the number of degrees of freedom, and therefore you have to deal with the full three-dimensional situation, which is going to be more complicated. That is the meaning. So non-holonomic systems are naturally going to be more difficult to solve than the holonomic system. So now we will come to the left-hand side, where we have written that the equation of the constraint will be known to you. So the one which is corresponding to the left-hand side, namely when the constraints are present, we have further conditions that is going to give trouble. And the simplest situation is where you know the equation of the constraint properly. So that is the simplest thing, and therefore I will write down that particular case first of all. So this is the one where I will put a right side arrow here, and then write down that the equation of the constraint is known. So because this is the well-known thing, which is if it is known, then the classification is clear, and then we can proceed with the reduced number of degrees of freedom. That is why I am writing this particular case as the first one. So equation of the constraint is known and it is an equality. It is an equality relation. This is the first condition. In addition to that, in order to avoid further confusion or further complication, there is also a demanding condition that it should not depend on velocity. So let me now specifically tell what is the special situation. You know that the equation of the constraint is a equality relation. That means you should not have something greater than 10 like that. Greater than should not come, less than should not come. Then it is called inequality. So equality relation means just like an equation of a circle, x square plus y square equal to 10. So you have an equal to that. So that kind of a relation should be there, which means greater than, less than condition should not be there. That is the one requirement. Second requirement is your equation of the constraint should not contain velocity. That means only positions should be allowed. The velocity or time should not be present in the system. I will explain why it is not so, why it is not, it will give trouble, why velocity should not be there for this one. Now, if this particular condition is satisfied, then we classify the constraint as holonomic constraint. So the name of the constraint is holonomic constraint, or if you are talking about a system, then it is known as holonomic system. Okay, we can use the word system or constraint. If you're asking the name of the constraint, then it is holonomic constraint. If you're asking the classification of the system, then we say holonomic system. So both of them, you can use the word holonomic. So let us put a box for this particular classification. So this is one of the most straightforward situation where the solution can be done with a reduced number of degrees of freedom. So that is why let us write down here. So it's very clear that on the left side that you have written is the one corresponding to holonomic, and the one written on the right side is a very clear cut situation where I do not know any equation. That's a non-holonomic system. Okay. So now what happens if you are going to deviate the conditions that are written down in this box, namely the holonomic. So this is a perfectly holonomic system. So if you are going to deviate from whatever is written in this box, then once again this will be written, or this will be classified under non-holonomic system. So to make that clarity, let me put a straight arrow from here. So we are coming down here. So I am taking it from the top one because the top one is the one that is corresponding to the general one. See here, you see this is the constraints are present. So from there we are straight coming down without going to the right side. Okay, once you go to the right side, you have the clear cut holonomic constraint. So now we are coming to this particular situation where the equality, or the what we say opposite to equality, we will say inequality relation. I'll write down that inequality relation for constraint. Suppose if you are going to have a physical system whose constraint equation is given by an inequality, then that particular system is known as, once again, non-holonomic. So it is the same non-holonomic that was there here. So once again, anything which is not clear or which is not possible to reduce, okay, anything that you say that I do not know what to do, then everything goes to the most general situation where you will be dealing with the full number of degrees of freedom. That is what we mean by saying the non-holonomic constraint. Non-holonomic constraint means it is a constraint that is not going to help you to simplify the problems or to reduce the difficulty level. Okay, you have to deal with the full difficulty. That is called a non-holonomic. So this is one situation where you cannot reduce the number of degrees of freedom. So another situation is where the velocity is present. So I can write down explicitly. Of course, even though that is visible, whatever we have written in the previous box, we can write down for clarity once again like this. When the equation of the constraint depends on time explicitly or on velocity. If any of this kind of thing happens, then once again the system will be classified as non-holonomic system. So these are the main classification. Our conclusion, therefore, after seeing this particular discussion, what is clear is that we are going to make two major divisions, namely holonomic and non-holonomic. So in that, the most important thing, the definition you should know is the one corresponding to the pure holonomic system, because that is the one which is going to help you to reduce the number of degrees of freedom, and therefore this is the one that you have to give attention. And whenever this is not satisfied, then everything is coming under non-holonomic. So you don't have to remember box by box in the way in which I have written. How do you remember is, only when the equation of constraint is well defined with an equality relation, and when the time and velocities are not present in that equation, then it is clearly defined as holonomic system, for which your equations are simplified, and therefore it will be more convenient to solve the problem. If anything is deviated from this condition, then you will be classifying under non-holonomic system. That's all. That's all about it. So it's all how do you write, whether in the form of flowchart you write, or you can write down in the form of a paragraph. So that's up to you. But ultimately, this is the point that you have to remember. Okay. So what is the purpose of the constraint is very clear. That the purpose of the constraint is ultimately going to help you to reduce the number of degrees of freedom, which means that you are going to reduce the number of Newton's equation that you are going to write down. Now, technically, reducing the number of degrees of freedom is known as elimination of dependent coordinates. So let me write down, therefore. So what is the consequence of this constraint? Whatever I explained, let me write down as a one sentence so that it will be easy. So that's all. So I have written what is the consequence of having a constraint or having a holonomic system particularly. Okay. So what is an advantage of having a holonomic system is that the equation of the constraint will be useful for the elimination of dependent coordinate. So this is the technical word that you have to pay attention to. And the meaning of this particular statement, elimination of dependent coordinate, what is the meaning is, finally it means that we are going to reduce the number of degrees of freedom. Okay. And by the way, I have not explicitly said the definition of a number of degrees of freedom. So basically, what is the meaning of degrees of freedom is, it is the number of coordinates that are required to specify a system completely. And that's all. So it is very simple definition. Maybe that also I will write down here. So that is the definition. So degrees of freedom is quite straightforward and simple to understand. It is the number of independent coordinates required to specify the state of a dynamical system. State of the dynamical system means you are going to specify the position and velocity, q and q dot. So that's what we started, right? We started with q comma q dot comma t. At a given time, you have q comma q dot, right? If you know the value for q and q dot for a given time, that is called one state. At another time, you have the value for another q and another q dot. That is called a second state. So the state of a dynamical system is an instantaneous. Instantaneous means at a given time. At a given time, this is my q and q dot. At another time, another q and another q dot. That is called the state of the system. So if you are able to specify the state of the dynamical system, then for that, how many coordinates are required? That is the number. That minimum is number, not, you should not take maximum number. The minimum number of coordinates required. Now, how do we know that it is minimum? That is the word independent. If you have dependent variables, then you have to eliminate. Okay. If one fellow is depending on the other fellow, We don't want a fellow who is depending on another fellow. We want people who are capable to work independently. For every job, you should not depend on another person. If I give you a job, you yourself have to do without depending on another person. If you are going to depend on another person, then you will not be considered. You will not be considered at all. That's the meaning. So you are going to eliminate. You will be eliminated. That is what is written here. So you see here, elimination. So what are you going to eliminate is, if anybody is there who is dependent in nature, who is going to depend on another fellow, then that fellow will be eliminated. Okay, so that is to do this job, constraint is required. Okay, that's therefore constraint in what way it is useful is, we can find out who is the dependent fellow and we can eliminate. And once you eliminate, number of degrees of freedom comes down. So that is the ultimate thing, and this is the main thing that is required. What I will do in the next class is that we will see one or two examples under each category. Holonomic, take one example. Non-holonomic means what are the possible examples that can be seen. And then I also told you that the number of degrees of freedom can be reduced. So if you are going to reduce the number of degrees of freedom, how to write that equation? Maybe before closing the today's topic, I will also write down so that it will be easy for you. Mathematically, we write like this. How are you going to reduce this? Because this is independent means everything is reduced, and then ultimate final thing you have, and that is the minimum number. So for your information or for you to remember, I will also write down that this is the minimum number of coordinates. That is the meaning. It is the minimum number of coordinates. How you have got the minimum number is, you start with the maximum number. So what is the maximum number? 3 times n. Okay. N number of particles are there. One particle requires 3 dimensions. So 3 times n is the maximum number. That's all. Not more than that. For a particle. Remember once again, particle. If you are going to discuss anything with the solid object or rigid dynamics or rigid body, for example, 3 will not be sufficient. Okay, because moment of inertia will enter into picture. For a particle, you don't consider moment of inertia. So that is why for particle dynamics, this is the case. So 3 times n will be the number of degrees of freedom. That is the maximum number of degrees of freedom for a unconstrained problem. And if I am going to perform a constraint, I am going to reduce. Reducing is called minus. I am going to put a minus here. Minus, you put an S, for example. And you give the name. What is that S means? This is the number of constraints. Number of constraints, or if you want to be mathematically accurate, then you say that number of constraints equations available to you. So you need to have equality relation. Once again, remember what kind of equation means. You should again explicitly tell that the equation should be in equality relation. Then only I will consider. If I have inequality relation, then that is rejected. You can't use it. So I must have equality relation. How many of them you have? That is the number of constraint equation. And also that equation should not contain time. Also that equation should not contain velocity. If you have such equations as the equation of constraint, then you count here number, that many number, you subtract. So if you subtract, what happens? You reduced, and that is the minimum number. Maximum number is 3n. 3n is maximum number. You subtract whatever possible because of the constraint, and what is left out is the minimum number. And that minimum number is called the degrees of freedom of a dynamical system. So probably this is the place I will stop. And there is one more small classification is there, depending on the time dependence or time independence. That part I will explain in the next class together with some examples. Okay, we'll stop here.